If we want to have a productive problem-solving lesson and a meaningful conversation that truly promotes deep conceptual understanding of the mathematics, then we need to plan carefully for these lessons. Margaret Smith and Mary Kay Stein have spent decades researching what works in this type of lesson and have condensed their findings into the book, The 5 Practices for Orchestrating Productive Mathematics Discussions. We use the 5 practices approach for planning and implementing problem-solving lessons in the Alcoa Champions of Maths program. The 5 practices are anticipating, monitoring, selecting, sequencing, and connecting. But before we can begin these, there are 2 things we must do. Clearly identify the mathematical goal of the lesson and choose a rich and demanding task that suits the goal. Now, the order in which these 2 things are presented, identify the goal and then choose a task that fits the goal, is held up as the ideal approach, and it is very suitable when sequencing a program of work and you are covering this particular topic and you need to cover a certain concept. So I know I want to teach this concept and I pick a task to suit. However, there is not always a good task easily available for every concept, but in every good task, a strong mathematical concept can be found. So often it is actually the other way around that people do this. They find a good task and then they look at which part of the mathematics in the task suits their program or their content and highlight that in the discussion. Having picked a good task and clearly identified a goal, the first thing to do is anticipate the student responses to the task. So you want to think of likely ways that students will try to solve the problem and plan your response. And in order to do this, the first thing that you must do is solve the problem yourself. In the process of solving the problem, you think about strategies that your students are likely to use and places that they are likely to go wrong. How you might help them get back on track when they go off course, and how you might help them move to more efficient or more sophisticated strategies when they're on the right path. The 2 images here are part of a lesson plan provided by one of our teachers for a lesson that she ran around this task from Challenging Mathematical Tasks by Peter Sullivan. How many small squares have been used to make this shape? Find the answer in 2 different ways. So the mathematical goal that might be here in this task, I would say, is around rectangles, area, and multiplication, and the connection between those ideas. So let's have a look at how she's thought her students might approach the problem and what she's thought she would do with them when they do. Counting and crossing off squares one by one. Absolutely, some of our students might simply count every single square in the image. Her response, can you break the shape into rectangles, or how many squares are in each rectangle, is moving them away from counting into looking at a more efficient way by using rectangles. So she's prompting the efficiency in that response. Counting by blocks of 10. So this is more efficient than counting altogether. And again, she says, can you make larger groups of squares to count together? So she's pushing them again towards the rectangular idea and a more efficient approach. But you can see she's changed the type of question she's using depending on what she's getting from the students to relate to where they're at. Break apart the shape into rectangles, calculate, and then add together. So this is likely one of the most efficient ways to solve the problem. Break it into 2 rectangles. Look at the length and width of each rectangle, multiply them and add them together to give you a total number of squares. So instead of pushing them forward in her response here, the questions that she asks, can this only be broken up this way? Explain why not? Does it matter which rectangles you use? What is important? These questions are getting them to think deeply about the mathematics. Is this the only way that you can do it? Is it the best way? If it is the best way, why it is the best way? So now she's getting them to think flexibly and think about efficiency. The fourth option that she has here, rearrange the shape to make one large rectangle. So the question she asks here is this a more or less efficient way than calculating rectangles within a shape? Why or why not? Notice she doesn't tell them either way. And in this case, it may or may not be more efficient. If the student is very strong visual reasoner and they're able to manipulate visual objects in their mind quickly, then this could be a very fast way to solve the problem by moving some of the rows from the top and rotating the rectangle on the right. You can rearrange the shape so that they're all in rows of 10 and then just do it in one calculation. If the student's visualization isn't as strong, then the strategy in the line above may be more efficient for them. Now, after having launched the lesson, during the lesson, we monitor, which means we move between the groups while they're working at their whiteboards, and we talk to them about what they're doing and look at their work. We make notes about which groups have used which of the strategies we predicted and which groups, if any, have used strategies we didn't predict at all. And then we will offer prompts or questions based on what we anticipated usually to help them move forward or get back on track. Next, toward the end of the explore phase, before going to the whole class discussion, we select and sequence which groups are going to present to the class, and we select those groups based on which strategies they used and what mathematics we want to highlight and what connections we want to make. So we order them in a specific sequence in order to make logical links. And there are different reasons why we might order and different ways we might order. So we might first look at the solution that most groups used so that they can relate to the mathematics that's being discussed. And then we may introduce a solution that is more unique and ingenious that maybe only one of the groups came up with, but is actually more efficient or quite elegant, and then make connections between those two strategies to help students to see how they could use either. Or we might look at a concrete solution, a pictorial solution, and then an abstract solution, and make connections across those different representational solutions. Or we might look at a common mistake or misconception that came up and address that first before going on to look at a correct solution and an effective solution. And then we might compare the two, looking at what is it about the effective solution that makes it work in comparison to the mistaken solution. So I've already begun to describe the fifth phase in terms of how we connect across the different solutions that are presented by students. In this phase, we really want to make all the connections we can. So we want to connect across solutions. We want to connect mathematical ideas, such as the rectangle, area, and multiplication in the first task that we saw. And we want to connect across representations. We also like to connect to other problems. So how could we use the strategy we've learned today in a problem we've seen before, for example, or how might we use this in another area of mathematics or in another real-world situation? So the photo I selected here reminds me of an example of a very good connecting discussion that was held in a Year 2 class. So this class was given the task of finding out how many bananas. They were told that there were 5 banana trees, and in each banana tree there were 2 bananas. Now they're a Year 2 class, and they were at the very beginning of Year 2, so straight out of Year 1. So good level for their age group. And what most of the students did is what we predicted, which is that they drew banana trees, drew bananas in the trees, and counted them, and got 10 mostly. So this student, Jack, although the class hadn't covered arrays, had knowledge of the use of arrays and saw that it was an appropriate way to solve this problem. So he drew an array, which led him to see how to use multiplication to solve the problem. So this is great because this is the most efficient way, and great to be moving students at that year level towards thinking about multiplication and the use of arrays. So what the teacher did is she discussed the first solution, the drawing of the bananas and in the banana trees and the counting. So this was the accessible one that most students had. And then she got Jack to come up and share how he solved it and show his array. And the way that she connected Jack's work to what most of the other students did was to ask him the question, in your array, can you show me where the bananas are and where the trees are? And he said, yes, sure, which is why those 5 columns are circled. He says each one of these is a tree and each of the dots is a banana. Now this is great because it connects to the students what they've done and helps them to see and make sense of this new strategy in terms of what they've done. That's the process of connecting. Now there's even more connection that goes on because it's very easy to see from his diagram, and he demonstrates by placing the 2's underneath each column and showing the addition to show how this is like 2 plus 2 plus 2 plus 2 plus 2, but how this is also equal to 5 lots of 2, which is 10. Fantastic. Question: what kind of messages are promoted by the practices you have seen in this video?